consensus team at Category Labs. Really excited to be here today to present to you MonadBFT. Just as a little background, MonadBFT is a variant of the pipeline hot-stuff protocol. To those that are familiar, DMBFT, fast hot-stuff, and Jotion are all variants of the pipeline hot-stuff family. We chose to further optimize and advance pipeline hot-stuff because they first offer high throughput, they have low finality latencies, and they're very simple. Their high throughput comes from the fact that you're pipelining your consensus rounds and having the next leader collecting the votes for you. The finality is achieved as soon as you get QC over QCs, so in 2 rounds from your original proposals. And it's very simple. You have a fan out, fan in, and every round of consensus will proceed like that. So that's the first version of BFT that we implemented, which is a variant of fast hot-stuff. And here's what we have observed on testnet. So Monad testnet is a validator network with 99 globally distributed validators. But as you can see on the proposal history diagram, every skip blocks sort of appear in back-to-back pairs, right? There's only one offline leader at that time. It's not actually 2 leaders timing out back-to-back. But you do see 2 skip blocks whenever there's only 1 leader offline. So that got us thinking, why, right? And I want to show you and help you to build intuition on understanding why that's happening and how MonadBFT solves that. So just to provide some background on pipeline hot-stuff. Pipeline hot-stuff occurs in this one-to-all, all-to-one, fan-out, fan-in fashion. So every round of consensus, there's 1 leader globally elected. In this specific example, that's Alice for round R. It will construct a block, Raptor cast it to the entire network, and the network will cast its vote to the next leader. Just for some more backgrounds on RaptorCast is also a consensus-wise consensus/network advancement by Category Labs. It features a 2-hop network message for block propagation. On the first hop, the proposer will Raptor encode its own block and assign the chunks to all the validators for a second layer rebroadcast. It is efficient and also equitable because everyone is contributing upload bandwidth according to their stake in the validator set. OK, so back to pipeline hot-stuff. After Alice sends its proposal to all the network casts their votes to Bob, which is the leader for the next round. Bob will create what we call a quorum certificate, or QC. That is essentially an aggregation of all the votes that has been casted on Alice's block. It is a self-contained proof that enough people have seen and agreed to vote yes on that block. After collecting that QC, Bob knows it's its turn to make its own proposal, so it will repeat the same pattern of broadcasting it to the network. Everyone will see Bob's block. If they agree to vote yes on it, they'll cast the vote and send their votes to Charlie, which is the R+2 leader. So this really simple fan-out, fan-in fashion is what powers pipeline hot-stuff. The message complexity of pipeline hot-stuff is obviously linear. You are only sending and processing linear messages per round of consensus, and that's really crucial to reaching a higher validator count and reaching globally distributed consensus. Just to give you more intuition, I'm going to show you a quick animation of how pipeline hot-stuff works. So this is a network configuration of 4 nodes, and the leader schedule goes counterclockwise. So right now, everyone casting their vote to node 4. Node 4 is sending out its proposal, and it will follow this pattern for eternity, hopefully. But that's not always the case. There are situations that can cause a leader to go offline. A leader might choose to delay its proposal to capture more MBV to pack more transactions into its own block. So let's look at what happens when there's a timeout. Back to the first example, Alice is making its own proposal to the network, and the network is casting their votes to Bob, the next leader. But here, Bob is offline. What will happen is the network will have their local timer that's timing every consensus round that they locally see. Once they hit the timer, they'll send a timeout message to every other node in the network. So this timeout process is actually quadratic. What the actual round they'll time out first is actually Alice's round, because every leader has two responsibilities in every consensus round. It's responsible, one, for collecting votes for its previous round, and two, making its own proposal. So in this case, Bob is offline, but we're timing out Alice's first because Bob has failed to collect the votes for Alice. After everyone has timed out Alice's round, they will proceed to time out Bob's round. So that's why you get the back-to-back pairs of timeout round or skip blocks in the first animation that you see for testnet. After it's all collected and we finally reached an online leader, Charlie here, Charlie will build his own block. What's interesting to note here is that the block Charlie will build will not be on top of Alice's block. And that's because there's no quorum certificate formed for Alice's block. And that's sort of the artifact of the fact that we are sending all votes to Bob. So what Charlie will do is build off its block off of the highest QC it has observed, which is over block R minus 1. So essentially what we've seen is a tail fork, a forking around the tail of the blockchain. Even though Alice is an honest leader, its proposal got enough support in the entire network, the block got abandoned only because Bob is offline. Just to click into more why tail forking is bad. First, it's terrible because it opens an MEV exploit. In the previous example, we were looking at how Bob, as a benign offline leader, can abandon Alice's block. It's also possible, as a sophisticated attacker, to intentionally wait for the previous round to time out and intentionally not to collect votes for your previous round so that you can unbundle their block and capture the MVE opportunities in your own block. That is awful for pipeline hostile protocols. Second, obviously, there's lots of rewards for Alice. Alice has done all of its validator duty, but it's unable to capture the rewards. It's bad for network throughput, and it's also bad for UX because now, because of tail forking, we need 2 rounds of consensus to gain confidence on the block's finality, whereas without tail forking, we only need 1 round. So MonadBFT aims at solving all of these. Most notably, we're providing tail forking resistance. It's a very strong guarantee that the honest proposal with enough support never gets abandoned. On top of that, since we're only modifying the unhappy path of pipeline host stuff, we inherit all the good performance guarantees on the happy path. Namely, those are optimistic responsiveness, where the protocol progresses at network speed, and linear message complexity on the happy path. So just to give a little more intuition on how MonadBFT achieves tail fork resistance, we are including 2 more fields in the timeout process, namely tip and tip vote. Tip is the latest consensus block that you have seen and agreed to vote yes on it, and tip vote is a vote signatures that you will cast on that block. So if Alice's block or any validator's blocks has gained enough support in the network, enough support meaning there's enough validators agree to vote on that, the next leader is forced to either form a quorum certificate directly from a supermajority of tipped votes, or it's forced to repropose the original highest tip, which in this case, Alice's block. Only in the case where Alice's proposal doesn't reach enough support will the next leader be able to move on and make its own fresh proposal. So that's how we are providing tail fork resistance, is by forcing the next leader to either form QC or repropose or otherwise prove that the previous leader's block didn't gain enough support. Now, MonadBFT is live on testnet 2. It's a larger, even larger validator network running Monad with over 180 validators globally. As you can see already, on the proposal history, we've eliminated the back-to-back timing out of skip blocks, and we are always salvaging the previous rounds. Now let's shift gears a little bit and talk about on engineering how we are implementing MonadBFT. We really took the idea of functional core and imperative shell in our design, where the core of our consensus client is Monad state that captures all of the core consensus protocol. It's purely functional. If you give it the same pre-state, the same inputs, it'll always emit the same post-state and same output. And it has completely no side effects. It's not sending any network messages directly from Monad state. It's not arming a timer from within Monad state. All of the side effects are handled by this imperative shell, which what we call the executor. So the run loop of Monad node or the validator client is really simple. There's really three things that we need to do over and over again. The first one being fetching an event from the executor. Second, passing that event to Monad state for execution and to update Monad state. And third, if there are any emitted commands that are side effects Monad state want to apply to the environment, we'll pass it back to executors for execution. So as a concrete example, you will receive, let's say you receive a proposal from the network that will be emitted from the executor in the form of an event. You pass that to Monad state through this update function, and Monad state, if it agrees to cast a vote on it, it will emit a router command, which is an instruction to the executor to send a vote to the next leader. There's several benefits with this design. First, it makes our code very comprehensible, the core consensus code. The inputs and outputs are very explicit in our code in the form of events and commands. It's perfectly deterministic, given the same input and pre-state. We will always get to the same post-state and outputs, and there's completely no side effects in Monad state. And we took this one step further and think about how we can increase debuggability and testability through this design. And that's why we create MockSwarm. MockSwarm is a simulation environment where we are only thinking about virtualized time. There's no wall clock timer involved. There's no network communication involved. That allows us to simulate many rounds of consensus very quickly and trigger different code paths in the core consensus protocol. So concretely speaking, we have a globally serialized order of events that's in the form of this event priority queue, and it's ordered by timestamps. Every time we'll pop the first event off of the queue, pass it to the corresponding mock node for execution, and the result will get appended back to the queue. So the mock node, the difference between a mock node and the real Monad node, the validator client, is that the executors are slightly different. Instead of sending packets over the real network, it's emitting an event to other mock nodes and for them to process it. The next thing we want to solve is how to build intuitions on consensus protocols, because they can be quite difficult to understand concretely. And that's why we built MonadBiz. So now I'm going to show you a quick demo of what MonadBiz is, and hopefully that can help you build more intuition around consensus too. So if you still remember, at the very beginning of the talk when I was showing the happy path, we saw the same diagram. It's not just an animation of the consensus protocol. It's actually Monad state, the core consensus code, compiled into WASM, and is running live in your browser. So here we can just see the nodes exchanging messages with each other. There are a lot of things that you can configure in this network. You can configure the number of nodes. You can change how the network latency profiles have dropping messages to different states, making state go completely offline, and there are just various things like network disturbance you can introduce to this simulation environment. It is also completely generic that nothing in Mock Swarm or MonadBiz is specific to Monad type events. If you have a consensus protocol, you are able to wire it up and visualize what's going on in the network. So what just happened now is node 4 just went offline, and people start timing out and send timeout messages to each other. Now, even though it's node 4's round to propose, it's unable to do so because it's offline, they'll time out again. But even though there's 2 rounds of timeouts, rest assured that node 3's proposal got salvaged because everyone has seen node 3's proposal, and they'll form a QC locally. So when it's finally node 1, that would be Charlie in the first example. When it's their turn to propose, they'll extend the honest leaders block. Just one more thing I want to show you with Mock Swarm is that, or with MonadBiz, is that you can actually go backwards in time. So if I were to go forward, it would look like proposal going out. I can actually go backwards in time, like so. And that's not a feature of Mock Swarm. Mock Swarm, we never take snapshots of any state, so things will only go forward. This is actually enabled by so every time you drag the slider from the future to the back, it's actually running a resimulation from t equals to 0 to t equals to your new tick. And that's only possible because Monad state is perfectly deterministic. Then you are able to see this backwards animation. So that's the end of the demo, if you don't mind switching back to the slides. So MonadBFT paper is available on archive. Feel free to check it out. We also feature a few blog posts on MonadBFT, more technical details, and on MonadBiz, specifically the visualization framework. There are also RaptorCast blog posts to check out if you're interested. MonadBFT just went open source this week, so feel free to check it out. MonadDebugger/MonadBiz is what I just showed. You're free to make any changes to the network. OK, that concludes my presentation on MonadBFT. Thank you. I'm happy to take any questions.
Hey, Michael, thanks for the wonderful presentation. How do you prove that? How does a round leader prove that they have, like the previous round does not have a quorum certificate? If you do this optimistically, then how are you doing this with low latency?
So I'm not sure. OK, I'll try to do an explanation. Just let me know if that makes sense to you. During the timeout process, every node will share the highest quorum certificate they have observed, and the lack thereof is the proof that there's no quorum certificate formed, if that makes sense. Thank you.
Yeah, so My question is now, right now it's a pure theoretical analysis, right? I believe the Monad testnet already running for some time. So based on the sort of the real data points for the testnet, what kind of like the maximum number of nodes we can expect for Monad midnight in the near future, and also in theory, so what kind of the best latency we can expect like once the Monad midnight is live?
So for testnets, for the two testnets that we have, as I mentioned, one have 99 validators and the other one have 186, I believe. That is the network size we're currently comfortable with shipping. And in terms of latencies profiles, that really is dependent on the geographic distribution of the nodes. If the nodes are closer together, you obviously get better latency profile, but that's not what we want. What we want is a globally distributed network. So right now, our network is producing blocks at 400 milliseconds, and that's the configurable block time that we want, so that nodes from different areas of the world can get participation.
Okay, I have a question related to your example when you show that A have the quorum certificate in this case, and but how we can trust the nodes that they show like the same? I mean, the honest nodes can be separated to the few groups or as many groups as it can, because like the A can be malicious in this case. So I mean, like how the security property works in the case that A produce few blocks or all of the things around it. What's the math related to the safety? Did it steal 1/3 of malicious assumption? 1/3, I mean, like 2/3 plus 1 honest assumption, or it's changed?
Yeah. So the security guarantee of like Byzantine fault tolerant isn't changed with MonadBFT. You asked a very good question. You're asking about what if Alice is malicious and it's trying to equivocate, and by sending a different proposal to different parts of the network. First of all, it's a slashable offense, and we're able to collect evidence for any equivocation. And second, during reproposal, the honest leader will only repropose one of the original equivocation. And if like that's on the assumption that if that equivocation has reached enough support. If it hasn't, it will proceed with collecting a no endorsement certificate, which if you're interested, I'm happy to delve into later. It will move forward with a no endorsement.
Great. Thank you very much for the great talk. I have a question regarding the leader election. What is the current logic that will determine who is the next leader or proposing the next block?
Right now, we are using a deterministic, like pseudo-random weighted round robin. So that's the current leader election protocol that's live. In this visualization, we just use round robin and to just visualize it better, since everything can go counterclockwise.
Thank you.
Thank you.